Yeah, welcome everyone to the second part of the lectures. I hope you enjoyed yesterday because we'll have more today. And don't worry if you didn't understand something. I mean, sometimes these conjectures deal with very different topics. So even if there is something of yesterday that is not clear, that will not make you be lost in this lecture. I mean, you can still understand, I think, everything I will say now. So yesterday we discussed the most important conjectures, at least the original ones, which is the absence of global symmetries, and try to discuss what do we mean with global symmetry, since this is the tricky part, and the relation that it has with the completeness hypothesis and the more modern approach about triviality of the coordination group. And then we spend the second half on the weak gravity conjecture, which has received a lot of attention in the past few years, as we will also discuss today. So before moving on, let me ask if there is any question about yesterday that you would like to ask. Okay. Okay, good. So then let's continue. Okay, so the topic for today is going to be first the distance conjecture. So here we're going to discuss another conjecture, which was formulated completely independent from the others. But in the past year, we are discovering that they are actually related as well. So let's see what this is about. So the distance conjecture is a statement about the asymptotics of the modular space. Okay, so in string theory, every coupling, mass, and so on is parameterized by the vacuum expectation values of some scalar fields, which are called the moduli because they are massless to lead in order before introducing additional ingredients in your compactification. And that means that we can move on this modular space, we can change the vacuum expectation value of the scalar fields to prove different effective field theories. Well, I put here also that this is one of the reasons why there is this common law that there are no free parameters, because everything is parameterized by scalar fields. I think this doesn't apply only to continuous one, also for discrete free parameters, even if they are not parameterized by continuous scalar fields. One can also understand that they are typically gauged in string theory because of the absence of -1 for symmetries. But anyway, let's focus on the modular space. So yesterday, a very important lesson was that quantum gravity, it seems that doesn't allow for the presence of global symmetries. But if we can now move on the modular space and prove different effective field theories, one of the things that we could do, for example, is to try to engineer some global symmetry. So for example, if I have some gauge coupling that is parameterized by some scalar field, I can take this scalar field to a limit such that the gauge coupling goes to 0. And that would restore, in principle, some global symmetry. So if that's not allowed, something has to go wrong when you try to approach that point in the modular space in which the gauge coupling is 0. And what happens is that that point happens to be at infinite distance in field space. So it's not part of your theory. Now, the fact that you can approach the point in a smooth way, it means also that the effective field theory is breaking down in a continuous way. So it's not only that that point is at infinite distance, but also that the cutoff of the theory goes to 0 as the gauge coupling goes to 0 as well. Or if you wish, as you approach these boundaries that are at infinite distance in the modular space. And this is purely a quantum gravitational effect because global symmetries, especially approximate global symmetries, are completely fine in quantum gravity. In particular, I mean, even if you would say, okay, the point in which the gauge coupling is 0 is not allowed, but what about a very tiny gauge coupling? That's completely fine in quantum field theory. In fact, weakly coupled gauge theories are very nice because we can compute many things with them. And however, we know that that cannot happen in string theory. Like we cannot make this coupling as small as we wish. And that's purely by quantum gravitational effects that will make the cutoff going to 0. Okay, so one can wonder what happens more generally. So the fact that the cutoff goes to 0 was already, I mean, we could already derive this from the weak gravity conjecture, but you could wonder about more general symmetries or more general infinite distance limits. So what's happened? I mean, what happens if we try to restore some other global symmetry that has nothing to do with a gauge field? Or what happens more generally if we just try to approach some infinite distance boundary in the modular space? Okay, and this is what the distance conjecture is about. Okay, so the formulation is as follows. So consider that we have some modular space parameterized by the scalar fields in my theory, and we have some metric in this modular space given by the kinetic metric. So the conjecture by Oguri and Baffa several years ago is that there must be an infinite hour of states that become exponentially light at any infinite field distance limit, so that the mass of the states, let's be more explicit. So at some point Q, the mass has to decrease exponentially with the geodesic distance between the 2 points in this modular space. Okay, so that if I have a theory which is valid at some point P, and I approach one of these boundaries that are of the modular space, and I go to some point Q, then this theory at Q should differ from the original theory by containing this infinite hour of states that decreases exponentially in terms of the geodesic distance between the 2 points. Okay. So basically, it's saying that an effective field theory can only be valid for a finite variation of the scalar fields. Okay, when you try to make this variation very large, something goes wrong. And what goes wrong is that you get an infinite hour of states. Okay, so having an infinite hour of states is problematic for an effective field theory, especially because, well, part of the conjecture is that this infinite hour of states is weakly coupled. I mean, they really count as different species, and that implies a breakdown of the effective field theory, and it's a drastic breakdown. I mean, there is no way that you can integrate in these states and still have a quantum field theory in the same number of dimensions and with the same fundamental degrees of freedom. That makes sense. So it's really you need to go to the quantum gravity completion, maybe take into account stringy effects or grow extra dimensions and so on. Okay, so it's a drastic breakdown. And this implies that the effective field theories, as I said, are only valid for a finite scalar field variation, which is not sharp value. I mean, it's not 1 or 2 or 3. It's just it depends on what is the value of the cutoff, right? So from the previous equation, we just get that the maximum variation goes as 1 over lambda log of m Planck over lambda. Okay, so it's giving you a relation between the cutoff, the maximum cutoff of the effective field theory, and the maximum scalar field variation that you can describe. Of course, in order to make something with this conjecture, we need to be more precise in the sense that, for example, we need to give exactly what is the value of this exponential rate, no, of this lambda factor. So in general, in fact, in the conjecture and in the refinements, it's claimed that this should be some order 1 factor, because I mean, at some point, if it cannot be parametrically small, because otherwise you spoil the exponential behavior. But what order 1 constant factor is not clear, it's not specified by the conjecture. Okay. So if you take that this is an order 1 factor, it's true that if the cutoff is very large, it's close to the Planck mass, then this implies that the maximum field range is of order m Planck. Okay, but this is assuming that we are putting a very high cutoff. If the cutoff is lower, then you can have larger field ranges. So the million-dollar question for the case of the distance conjecture is, what is the value of this exponential rate? What is lambda? In particular, whether we can derive it from the data that we have in effective field theory. No? In the same way that with the weak gravity conjecture, we also had an order 1 factor, but was determined by the extremality bound of the black holes. So is there anything similar here? I mean, can we try to be more precise and give what this value of lambda is? And here is where a lot of research goes on at the moment. Okay, so and right now it maybe doesn't tell you much, but I put here some proposed lower bounds for this value that have appeared in the literature. Some of them are purely geometrical in the sense that they are based on some classes of string theory compactifications. Like you can go and compute what lambda is, and then you get universal bounds that apply, for example, to any Calabi-Yau manifold or things like that. But there are also some proposals based on the relation between the distance conjecture and other conjectures, like the weak gravity. For example, we will see that if the tower is charged under some gauge field, then one can also use the extremality bound of the black holes to bound this exponential rate for the distance conjecture. Okay, any question about this? Okay, so as usual, let's try to understand this with some examples. It's always better to have examples in mind and then try to go to the more general setup. So let me take our easiest and favorite example, which is just a Kaluza-Klein circle compactification. And then we have two possible infinite distance limits, right? We can send, so if this is the radius, we can send the radius to infinity, or we can send it to 0. And both are at infinite distance measured by the field metric. And indeed, as I guess all of you already know, when the radius goes to large values, indeed we are going to get an infinite tower of states that become light, which is the KK tower. Okay, Kaluza-Klein states will become light. But there should also be a tower that becomes light when the radius goes to 0. And this is something that happens in string theory, but that doesn't happen necessarily in quantum field theory. So in particular in string theory, what happens is that we have winding modes. We have extended objects, strings or branes, right, that are wrapping this circle, and therefore become light when the circle becomes small. So one could say that the distance conjecture is actually predicting the existence of extended objects that are wrapping these cycles in order to have some tower that goes to 0. Okay, so we can just do it more explicitly. So this is the Lagrangian for a dimensional reduction on a circle. D is the space-time dimension of the lower dimensional theory. So we just have to canonically normalize this field. So this is the proper field distance. And write the KK tower that goes right as 1 over R to some power in terms of this proper field distance, which taking this metric is just given by this. Okay, this is just easy piece of cake. And here we already have one result for what the exponential rate is. So here you can see that indeed it's some order 1 factor that in this case depends on the space-time dimension. Okay, so one of the lessons of this example is that the distance conjecture is linked to the existence of dualities. So the fact that we have these KK towers and these winding modes is a reflection of the T-duality in the circle, right? That they get exchanged when performing a T-duality. And this is indeed one of the, well, this is the original motivation of the conjecture. The fact that it seems that in string theory, every time we go to some asymptotic limit, there is some duality that becomes manifest. There is a new description that emerges in terms of a new tower of states that is becoming light. It can be Keiki towers, and it's associated to duality or S-duality, and we have strings and so on. So try to understand why the distance conjecture is true and why it should hold in quantum gravity in general. It's like trying to understand why dualities are always there in quantum gravity. So what is the meaning of all these dualities? Which is quite an ambitious question. Okay, so let me give you another example, which is very representative, together with the Kaluza-Klein decompactification, which is, for example, if we consider type 2A on 10 dimensions, that at strong coupling can also be understood as M theory on a circle, right? So we have the same. In this case, now is the dilaton, right, which is parameterizing the radius of the cycle, and it's my modular space is again one-dimensional. And the proper field distance again goes as the logarithm of this dilaton. So we can take two limits. We can take the limit in which the string coupling goes to infinity, or the limit in which the string coupling goes to 0. In the case of the string coupling going to infinity, it's something very similar to what we already did. We are going to have a tower of Keiki modes from the point of view of the M theory perspective. So this is like sending the radius to infinity. And from the type 2A perspective, it's just, as you know, the tower of the 0 branes, right? So we can indeed check that the mass of this tower of the 0 branes scales with the string coupling this way in Planck units. It's very important every time we are going to check all these examples. It's very important to go to the Einstein frame and express everything in Planck units, okay? Because everything is becoming light only with respect to the Planck scale. So that's why I'm doing this carefully. And if we write it in terms of the proper field distance, we get this other factor for the exponential rate. Okay, so the resolution in this case is decompactifying again. But what happens if we send the string coupling to 0? Well, in that case, what happens is that we get all the string excitation modes that are becoming light, right, in the tensionless limit. So the resolution is the type 2A string perturbative theory. Okay, so all the string modes, so the string scale goes to 0 when the string coupling goes to 0. And in terms of the Planck mass, decays exponentially with this factor. Okay, so I gave these examples just because they are the easiest ones to picture what this is about, and also because they represent the two types of scenarios that we also find in more complicated limits and compactifications. So there is a refinement, I would say, of this distance conjecture by Wolfgang here and collaborators, trying to specify what is the nature of the tower that is becoming light. Okay, so the original conjecture is not telling you where this tower of states is coming from, but so far it seems that on all the infinite distance limits that we have checked, the leading tower is either something that is like a Keiki tower in some dual frame, so it represents some decompactification limit, or it comes from a string that is weakly coupled and is becoming tensionless. And this is what is called the emergent string conjecture. Okay, remember that if there is any question, I'm very happy if you just interrupt me and ask. Also, I'm not putting many references, but in my lecture notes in archive, you can find these topics and you can take a look to all the references there. Okay, so let me make one comment I want to make. Sometimes talking about the asymptotic regimes seems confusing, and people typically ask me how large the scalars need to be so that you call it an asymptotic regime or not. Like, are you talking about 100 Planck mass, 1000 Planck mass? And the answer is that it's not about a number. It's the same notion that we have in quantum field theory about a perturbative expansion, right? So we are in an asymptotic regime. I mean, this exponential behavior should matter and you should see it, as long as you can think of as long as you can expand, right, like your geometry, or if you wish, your effective field theory in terms of powers, right, of this field that is becoming large. So it's nothing, I mean, it's nothing more than that. So it's not about a concrete number. It's about whether that perturbative expansion makes sense or it doesn't make sense anymore, and non-perturbative effects become more important than perturbative one, and so on. So that means that most of the string pheno models that we usually have, more of the model building that have been done in string phenomenology, is always at some asymptotic regime. Because in order to have computational control, we like these perturbative expansions, right? In order to be able to neglect higher order corrections. So we are typically always at large volume or weak string coupling or things like that, even if we don't say it explicitly. So the question that matters is not about how large is this field, but about what is the exact value of this exponential rate, because that will imply that that will tell you whether the effective field theory that you are constructing is valid at the energy scales that you want it to be valid or not. Okay. Okay, and there is also, just regarding this comment, I wanted to mention that there is something which is called the refined distance conjecture, which is the statement that this exponential behavior should be manifest when the field range becomes Transplanckian. So this is a statement not only about the asymptotic region, but actually about the bulk of the modular space. Because, I mean, you could wonder, okay, I mean, it's clear that at these asymptotic regions, we are going to have the exponential behavior, but you could wonder whether you can have still a parametrically large field variation moving on the bulk very far from these boundaries. Of course, you will never be able to engineer an infinite distance variation, but you can ask about what about Transplanckian field variations. And then this refinement is saying that you cannot engineer some Transplanckian geodesic distance without approaching one of these boundaries and getting sensitive to the exponential behavior. When talking about all the evidence, I like to differentiate these two statements, because we have already a lot of evidence for the asymptotic regions, because are precisely the regimes in which we can compute things, basically. But about the bulk is still, I think, a very open question, and there are no counterexamples, and in some cases in which we can have control of a better control of the full modular space, like in the complex structure modular space, this has been checked, but well, it's something we need to work more before claiming victory. Okay, any question? Very good. So I wanted to explain now what is the relation between this distance conjecture and the other conjectures that we saw yesterday. So, well, I already gave you some motivations between the relation of global symmetry and infinite distance. So it's clear that a global symmetry can only be restored at infinite distance. Okay, so whenever there is a global symmetry that is restored, you can understand the tower of the distance conjecture as a quantum gravity obstruction for that to happen. But it's not obvious at all whether the opposite is also true. So whether every infinite distance limit has some global symmetry restored there. And this is, I think, an open question of research. So far, all the limits that I could think of has this feature. But it's also true that all the limits that we check are typically coming from supersymmetric compactifications, in which we always have gauge fields or actions or things like this. So it's normal that there is some global symmetry emerging. Although in some non-supersymmetric setups, like the SO16 heterotic string theory, it also seems to be the case. Okay, so this is an open question, but if it happens, if there is, in particular, for example, if there is always some vanishing p-form gauge coupling at infinite distance, then we can relate the three conjectures. Because what's going to happen is that the distance conjecture, well, there will be a charged tower which will decay exponentially, so it satisfies the distance conjecture, and will also satisfy the gravity. So it's the same tower that fulfills both conjectures at the same time. And if that happens, then the exponential mass rate will be fixed by the black hole extremality bound. Okay, so just to come back to our favorite example that we have already given all the behaviors of the gauge coupling yesterday and of the field metric today, we can explicitly see how these two things come together. So if we have a Kaluza-Klein compacted Fourier, I already have the canonically normalized one, and we have the KK photon that has this dilatonic form, right? Like the radius is parameterizing the gauge kinetic function this way with these factors that they put here. The KK modes, we have seen that they decay exponentially in terms of the proper field distance. And we saw yesterday that they are also satisfying the gravity conjecture. So just to be precise, we can check exactly how the exponential rate relates to the extremality bound. So in order to do that, let's write what is this extremality bound. So remember from yesterday, there were two ways actually to define the gravity conjecture when there are massless scalar fields. One was in terms of some extremality condition, and the other one was in terms of a repulsive force condition. Okay, so let's do this. Now, the extremality condition, this is a formula I gave you yesterday, means that the charge to mass ratio of the states, in this case of these KK modes, has to be bigger or equal than the value of the extremal black hole, which takes this value here, and depends on the space-time dimension. So, in fact, you can do this as an exercise, but just, I mean, it's very easy to check that plugging this value of alpha here, you get that this is just equals to 2, which means that the gravity conjecture tells you that the charge to mass ratio has to be bigger or equal than 2. And if we take the charge that I gave you here and the mass, and you to compute the ratio, you get that indeed it's exactly 2. So the KK modes are extremal, taking this definition. And taking the other condition of in terms of a repulsive force condition, now what matters is not the behavior of the gauge kinetic function, but the behavior of the mass of the modes. This is going to be actually the same than the exponential rate for the distance conjecture, right? It's the derivative of over the mass. And if you plug this formula, you get that this is also 2. So what is happening is that the KK modes are both saturating the gravity conjecture in terms of an extremality bound, are also feeling no force, so they are saturating the repulsive force condition, and are also satisfying the distance conjecture with an exponential rate that is just alpha half. Okay, you can check this from the numbers, but the idea is that this, what is happening here is that this factor is equal to this one. So the exponential rate of the tower becomes related to the behavior of the gauge kinetic function. So the contribution from the scalars to the extremality bound is what determines the exponential rate. Okay. Okay, so this is just like a very easy example, but the same thing is realized in more complicated scenarios, as we will see later. It will always, I mean, this will always happen whenever there is a p-form chopping that is going to 0 at infinite distance, and this super extremality condition and this repulsive force condition coincide, no? In the sense that they gave you the same bound. So as I put here, if they coincide asymptotically, so extremal states also feel no force, then the exponential rate of the distance conjecture is bounded by the black hole extremality bound this way. I put bounded because it could be that there are other towers that become lighter faster than this charge tower. But if they decay lighter faster, then the exponential rate is going to be bigger. So this is always some lower bound for the distance conjecture, okay, which is also what we need. Okay, we need a lower bound to put an upper bound on the maximum field rate that we can have. So how general is this? It depends on how general is the fact that we seem to find some gauge coupling of some p-form gauge field always going to zero at infinite distance. So that we always have some weakly coupled gauge field theory description. This is something to answer in the future. Okay, any question? Okay, very good. I guess it's easier to think of the distance conjecture than the definition of global symmetries. Okay, so another way to connect the distance conjecture with the weak gravity conjecture is via this scalar version of the weak gravity. So it's a different approach in the sense that we don't assume that there is any gauge coupling that goes to zero. In fact, the opposite. If you just have scalar fields and gravity, you could still wonder if there is something similar to the weak gravity conjecture that should apply, meaning whether gravity should also be weaker than the scalar force. And this is what is called the scalar weak gravity conjecture, claiming that the gravitational force should be weaker in this case. Now, if this happens, it means that you should have some state whose derivative, which is the scalar charge, is bigger than the mass itself of the particle. And the order one factor is fixed such that it's saturated when it feels no force, when both forces compensate each other. If this is true, I mean, one of the interesting things is that in order to make this inequality valid for large field variations of the fields, you need that the mass behaves exponentially on the distance. So it's sort of giving you the exponential behavior of the distance conjecture. The problem of this is that there is no black hole argument as we have for the weak gravity conjecture, because I mean we don't have black holes that are not charged under some gauge field, but only scalar fields. So the bottom-up motivation for this is less clear. Okay, so in fact there are many works trying to understand this better and even proposing refinements, including second derivatives. So I would say that if there is some statement along this line that holds in general, it's not clear yet. It's an open question yet what it is. Okay, so it was just to give you some, so you can get an idea of what this is about, but this might change in the near future. Let's see. Okay, any question? Okay, so this is the relation with the weak gravity conjecture. So we have this option, which deserves more study, and there is also the relation whenever we have a gauge coupling, then it's clear what will happen. Now, the last thing I want to discuss is that so far I'm talking about variations in the modular space, so in a flat space where there is no potential. Okay, so we are just moving and proving the different effective field theories. But one of the reasons why this conjecture is interesting is because it can provide some bounds for large field inflation or this type of models, but it's very important then to understand what happens when you have a potential. Okay, without it, it's impossible to give any phenomenological application. So I wanted to discuss with you how this distance conjecture is modified when we lift some of the directions of the modular space. Okay, so first thing that is actually sometimes I didn't notice for some time, but it appears already in the original paper that the distance conjecture should hold not only for flat modular spaces, but for pseudo-modular spaces generated by the values of the potential. So why is this? It's because, I mean, when we talk about the modular space, and for example, some compactification of string theory, and we have some modular space, this modular space is also the bottom of the potential, right? That is giving mass to the string modes or Keke modes and so on. So, I mean, it's always about the bottom of some potential. And based on physical grounds, whether it is completely massless or just very light compared to the energy scales that we are interested in, so comparing to the cutoff of the theory, it shouldn't matter. I mean, there should be a way to connect continuously both setups. So the idea is that if you have some pseudo-modular space, in the sense that you have a nearly flat trajectory, which is much lighter than all the other scales involved in the problem, the distance conjecture should also apply there. Now, if you assume this, you can run into some puzzle that I put here. The puzzle is that it might seem that you are generating sometimes the distance conjecture at some energy scale and then violating the distance conjecture in the infrared, something similar to what we discussed with the gravity under dimensional reduction. So let's see the puzzle slowly. The point is that imagine that you have some UV modular space and flat modular space, which satisfies the distance conjecture. And now we add a potential over it. Okay, and we want to study if the distance conjecture is also satisfied in the IR modular space that is generated by the values of the potential. Now, I can engineer, and you can engineer potentials such that this will not happen, that the distance conjecture will not be satisfied. Okay, if we have, for example, that the value of the potential goes along a very non-geodesic trajectory from the point of view of the UV, then there will be no tower of states that is becoming exponentially light with that proper field distance. So then, I mean, the question is at what regime, at what energy scale should satisfy the distance conjecture, right? I mean, it seems it doesn't make sense alone if we allow any type of potential. And the only solution that is consistent with the conjecture to be consistent along the RG flow. So in order to guarantee consistency of the conjecture at any energy scale and be a principle of quantum gravity, is that it's not only constraining the modular space, but it's also constraining the types of potential that you can engineer in quantum gravity. So according to this, you should not be able to engineer some scalar potential such that the value of the potential, this IR modular space, has such a level of non-geodesity from the UV perspective such that the distance conjecture wouldn't be satisfied. Okay. So already the distance conjecture by itself is constraining what scalar potentials are consistent in quantum gravity. Any question? Okay. This is sometimes is not explained in much detail in other papers or reviews and so on, but it's actually part of the original paper. And I think what we are doing this year, that we are studying more cases for n=1, for example, is precisely try to see if this is completely general. So it's so whether we can prove that the distance conjecture will always be satisfied along these values. And I don't have much time. I mean, for the lack of time, I cannot discuss this in much detail. But for example, in the case of Calabi-Yau compactifications, when we have some fluxes and we induce some scalar potential, we can prove that at all the asymptotic limits, the potential behaves in such a way that preserves this homogeneity property here, which implies that the values of the potential actually preserve the maximum level of non-geodesity that would be consistent with satisfying the distance conjecture, which is, I think, a very highly non-trivial check. So if we think of n=1, and we have some complex scalar, right? We have a complex manifold. We have both what is called the suctions and the actions, so the periodic, the non-periodic, and the periodic scalar. And many inflationary models always use the actions to engineer large field ranges. So for example, you could ask what happens if, let's see, if this red line is the action, is my geodesic distance, okay? Even if this geodesic distance is small, I mean, what happens if I just try to go like in a spiral and engineer a very large field range, okay? What goes wrong then? Because the exponential tower, I mean, the tower will not decay exponentially with this field trajectory. And the point is that this type of potentials do not allow you to have this type of spirals when you are in the asymptotic regime. So that you are moving the same amount on the action, the angular variable, than on this action. Okay. And that's why if you have some tower originally that satisfies the distance conjecture for this action, it will also satisfy it in terms of this proper field distance that involves the action. Okay, no questions or complaints? Okay, so many more things have to be studied here. In fact, well, if you want to work on this, I think there is a lot of room to understand better what are these constraints on the scalar potentials that can arise just by thinking of the distance conjecture. Many new things will appear in the future. Okay, so last thing for the distance conjecture, and then we will go to the evidence in string theory. It's just, well, I wanted to say a few words about the implications for inflation. So one of the obvious implications of this conjecture is that it's constraining the field ranges that you can have. And for example, if we think of inflation, then the Hubble scale during inflation should be lower than the cutoff. So it's giving you some upper bound on the field range in terms of the Hubble scale of your theory. If we plot this relation, the thing is that it goes, it has the opposite behavior that what is the least bound, that is you need to satisfy in order to have slow roll inflation. So this is the field range in terms of the tensor to scalar ratio. And if you want to satisfy both things, so you have slow roll inflation consistent with quantum gravity, you only have a finite region that is allowed. Of course, what is exactly this finite region depends on what is exactly this value of 1 over lambda, and that's why it's so important to determine this factor in a more precise way. But already, I mean, for order 1 factors, one can see that there are models that are ruled out, and there are other models that are okay. So I would say that the conclusion is not that the distance conjecture is ruling out large field inflation, it's just constraining the models that you can have, okay? And of course, we need to answer this before going further. Okay, so with this I finish the definition and the basic properties of the distance conjecture, and I'm gonna start reviewing what is the string theory evidence that we have for all these conjectures, for the weak gravity and the distance conjecture. So if there is any question, it's a good moment to ask. Okay. Very good. So the next topic that I wanted to discuss here is the evidence that we have for the weak gravity and distance conjecture in more detail. Okay, I mean, it's very nice to understand the conjectures, but at the end, I guess it can be difficult to keep track of all the works that are appearing, and sometimes it can be very confusing to understand what parts are widely accepted or proven and what parts are more fuzzy and not so clear. So I tried to create some summary to clarify these points and so that I can transmit to you where we are confident about the results and where we need to work harder. So for the weak gravity conjecture, I put here a summary of the different works providing evidence for it. Of course, I cannot discuss each of these works in detail. And also, it's not the aim of these lectures. And actually, I mean, I'm going to focus on the evidence coming from the string compactifications, but let me mention that there are also works studying the higher derivative corrections to the black holes to show that they go in the direction such that the charge to mass ratio becomes bigger than 1. That could mean that already very small black holes are satisfying the weak gravity. There are also works using unitarity and causality also to show that this has to be always the case. A very nice connection with weak cosmic censorship. Some models that in principle could violate this, but they satisfy weak cosmic censorship when you satisfy the weak gravity conjecture. And also works in ADS-CFT, in which they relate the conjecture to modular invariance and other quantum information theorems and so on. So you can take a look to my notes in arXiv and look for references. And if you are curious about some particular points, you can ask me also, and I can tell you more about it. So I think all these works are telling us that at least something like the mild version of the weak gravity conjecture holds, like that there are some states that the charge to mass ratio is bigger than 1. But one of the open questions, of course, is what is the strong version? As we discussed yesterday, what is exactly the strong version that realizes in string theory, in the sense of whether we can ensure that there are light particles below the cutoff that are satisfying the weak gravity. In particular, what is the index of the sublattice? That if there is an upper bound for the index of the sublattice. Other open questions is all this interplay between the weak gravity, the repulsive force condition, the BPS bound. I mean, when we have scalar fields, try to understand better. I think there is a more efficient formulation of these things. Of course, we need to gather more evidence for non-supersymmetric states. It's always very easy to show that the weak gravity is satisfied when we have BPS states, but there are not so many examples in string theory compactifications that are non-supersymmetric. Also, the motivation for the weak gravity for actions, like a bottom-up motivation, is missing because the black hole argument applies for particles and other extended objects, but not for actions or low codimension states. So this is something to work on as well. And there are also works about the weak gravity for the case of discrete symmetries and not just continuous H groups, but you can take a look in my notes. Okay, so this is sort of the state of the art. And for the distance conjecture, the situation is a bit different. So the thing is that we have plethora of string theory examples. It's sort of sometimes it just seems a built-in feature of string theory that we always have this tower of states at infinite distance, but it's missing some model-independent bottom-up approach. In the same way that we have this argument based on black holes for the weak gravity, something along these lines would be also necessary for the case of the distance conjecture in order to argue that it's some general principle of quantum gravity. There are some attempts using, for example, some local version of the distance conjecture when you have some spatial variation of the fields and the non-compact dimensions, and then you can engineer large field variations starting from solitonic objects. But the conclusions are not. It's not conclusive yet. And also, in addition to the string theory examples, we have recent works also about the distance conjecture in the context of ADS-CFT. I was planning to discuss this in more detail, but I think it's a bit too much. So I just want to mention that there has been some recent works studying the distance conjecture in the conformal manifold. So now we prove infinite distances in terms of the Samolov-Hikov metric in this conformal manifold. And we have also conjecture based on the evidence that we have from CFTs that at infinite distance, indeed, we always find some infinite tower of states, if you wish, from the ADS dual. So we always have higher spin operators such that the anomalous dimension of these operators is going to 0 at the infinite distance point. And it's going to 0 exponentially, the same way that with the distance conjecture. And the diameter of this modular space then increases logarithmically, okay, in terms of this anomalous dimension. So, I mean, you can ask me more about it later, but let's just, from now on, let's try to focus only on the examples that we have from the string theory compactifications, okay? And also as other open questions, so you can keep in mind what we do not know yet completely is, what is this exponential rate for the tower? What is the nature of the tower? If we always have this emergent string conjecture or not? And as we discussed also, what are the constraints on the potential that we can derive from the distance conjecture? Okay, so this is all for the summary. And now what I want to do is to show you more complicated examples in string theory in which we have checked the distance conjecture and the weak gravity conjecture, so you get a flavor of the types of works that are done when you try to test these conjectures. Any question? Okay, you are very silent today.
I ask one at the end.
Okay, you should ask questions also, I mean, of the students, because otherwise I also have questions that I can ask for you on the break. So if I don't get any questions from the students, I think I will ask and you will have to reply using the chat or something like that. Let's see how it goes. Okay, so let's go for 10 minutes more and then have a break. I think that's good, right? It's 10 minutes before, yeah. Okay, so let's go through the string theory evidence. Okay, like as we said, formulating the conjecture is just the first step. The hard work comes afterwards. And in these past few years, which there has been this explosion about the Swampland program, I think we have made a lot of progress providing quantitative tests for these conjectures. Of course, there is a lot of work yet to do, but it's nice at least to know what has been done so far. So for the case, especially for the distance conjecture, so for the case of studying asymptotic limits in the modular space and see what happens with these towers of states, whether they satisfy gravity, whether they satisfy the distance conjecture and so on. There has been a very systematic approach. So for the case in which we have more than 8 supercharges, actually the modular space can always be understood as a coset space. And by Chicotti here, the distance conjecture, the fact that we have, in this case, is going to be PP states that decay exponentially in terms of the proper field distance, has been proven using just some group theoretical arguments. Okay, so more than 8 supercharges is kind of trivial that the distance conjecture is satisfied. Now, in the past few years, there has been a lot of study for cases of 8 supercharges. Okay, in which the conjecture is not so trivial because the modular spaces are a bit more complicated, and we can have many different types of infinite distance limits. In particular, there are works about the 4D n equals 2 theories that arise from type 2 on Calabi-Yau 3/4, and then about 5D and 6D n equals 1 and theory of theory compactifications on the Calabi-Yaus. So I'm going to discuss these cases in more detail, but let me also mention that I think this year, now that I think we understand better what happens with 8 supercharges, we have continued with the case of 4 supercharges and understand these conjectures in the case of 4D n equals 1 theories, which of course are more interesting for phenomenology. And in all these cases, it happens that at the asymptotic limits, we get these charged towers of states that are satisfying both the gravity and the distance conjecture. And one of the outcomes of all this analysis is that by trying to understand these conjectures and how they are realized, we are discovering very interesting connections to mathematics of algebraic geometry, modular forms, and so on. So sometimes these conjectures sort of tell you where to look. So it's sort of a guiding principle. It has triggered a lot of research understanding better the geometry of these spaces. Okay, so I'm gonna start just 5 minutes about the type 2 Calabi compactifications. Probably I can finish the vector multiplet modular space. So for the case of type 2 Calabi compactifications, the modular space to in order can be split in the product of the hypermultiplex and the vector multiplex. And there has been works in both of them. I'm going to focus mainly on the vector multiplet modular space because it's very representative about how the distance conjecture is realized and the possible limits that we can have. So the vector multiplex modular space is either the complex structure modular space of the Calabi if we are reducing type 2b, or the Kähler modular space if we come from type 2a. So if you don't know much about these compactifications, I hope that this can also serve you to learn a bit about them and how we work in string Fino. So in this case, it's just a 4D n equals 2 theory. So let me focus on type 2b for concreteness. We have our scalars that are parameterizing also the gauge kinetic function for our abelian gauge fields. As we said in type 2b, the scalars are the complex structure moduli, and the gauge fields, in this case, they arise from dimensionally reducing the C4 Ramon field in type 2b. And then we are also going to have BP states that are charged under this gauge field and correspond to, well, they are particles that arise from wrapping DC branes that were charged under the C4 in 10 dimensions. Okay, this is sort of a summary. And since we have the vector modular space of 4D n equals 2 theories, the modular space is a special Kähler manifold, which means that we can determine the metric in terms of a Kähler potential that can be written in terms of the periods of the holomorphic 3,0 form of the Calabi where a basis of symplectic 3 cycles. Now the BP states, as you know, the mass is going to be determined by the central charge, which is given also in terms of these periods, okay, and the Kähler potential. So anything, I mean, all we have to say is to be able to determine how these periods behave at different points of the modular space. Now, what happens is that when you go, when you try to engineer infinite distance, I mean, this can only occur if you are approaching a singularity of the modular space. And when you approach a singularity, from a physics perspective, this is understood as the fact that you have integrated out some state that is actually becoming massless. So there is some BP state that becomes massless at a singular point. And the question is whether there is indeed an infinite number of them or just a finite number of them when we go to infinite distance. So the picture that arises in these compactifications is that this is our modular space, and we have different singular points. Okay, not all these points, not all these singularities have to be at infinite distance. So, for example, the conifold point is a finite distance singularity. Okay, finite distance. While, for example, the large, what is called the large complex structure point, is at infinite distance in modular space. And the picture that arises is that these finite distance singularities are associated to a finite number of BP states that become massless, while the infinite distance are associated to an infinite tower of VP states. I mean, this might sound reasonable, but it's actually non-trivial to check that this is actually what is happening, okay, to prove this. So what we are going to do after the break is to show you how we can prove that this is the case and that indeed the distance conjecture is satisfied because there is always an infinite tower of VP states that become exponentially light at every infinite distance singularity. And that these VP states are actually extremal, so they are also satisfying the gravity. And to do that, we will use some algebraic theories of limiting Hodge theory and some counting of the VP states. So let's take a break, then I will explain this and some other compactifications in more detail, and then I think this will take us like half an hour. And for the next half an hour, I will discuss other conjectures like the ADS distance conjecture, the CERN conjecture, and so on, and how they relate to the ideas that we have already explained so far. Okay, I'm also going to stay around here, so if you have any questions during the break, you can also ask.
How long do you want to have the break? 10 minutes, 5 minutes?
5 minutes, I think it's fine.
Okay, so 5 minutes. Well, let me ask a question, but maybe you will address it anyway. So if it can also postpone it after the talk. Namely about potentials and long distances and this kind of things. You put it in a way as if a theory with a potential is a subcase of the theory without potential. Yeah. But say if you generate a potential by a flux.
Sorry, say again, I didn't.
You somehow seem to treat theories with potential as a subcase of the theory without potential. Yeah. I'm not sure how relevant this is for your proof, but say if you generate a potential by adding a flux, yeah, it's a very drastic and discrete operation like an orbifold actually. Yeah. An orbifold or a flux compactification will change the spectrum, can change chirality, everything. So once you do this, the theory will not be a subcase of some other high dimensional theory. So the discrete change of the whole theory. And actually the modular space for n=1 theories is not really a good manifold even. You know, it has all these sort of loci where deep brains or say open strings become massless and new branches open up. So you have a whole collection, a whole bouquet of branches with different dimension even. Yeah. So in this space, I mean, how do you make these general statements? Say what happened?
Yeah, no, I mean, it's true that turning on or off some potential is not some continuous deformation, right? Like we cannot just, like fluxes are discrete. So as you said, everything, I mean, there are many things that can drastically change. The point is more that, I mean, it already applies in cases in which there is a potential, like if we think of the potential like giving some mass to KK modes and so on, like in just some n=2 compactification, that's already the bottom of a potential. So why should apply in some cases and not in others? It's not about the fact that everything should be continuous and you should, like any IR modular space is a subcase of the previous one. That's not true. I completely agree. It's just that if it is a general principle, it doesn't make sense that there are exceptions or that it applies in one particular case in which the potential is about the KK scale, but it doesn't apply in other case in which the potential is about the flux, I mean, some flux scale. I mean, quantum gravity shouldn't care if you are talking about KK modes or string modes or KK scale, I mean, or flux scales or the TV scale. I mean, shouldn't care about the energy, right? So for me, the only way in which this makes sense is that indeed it doesn't matter. It should apply at any energy scale with any potential that you could engineer in quantum gravity.
So are there statements like what happens in a sort of in cusp points at, you know, asymptotic beams? I mean, for the n=2 situation, you know, where you have a very well-defined modular space, flat structure, everything, special geometry, whatever, there is very well defined, and one can classify all, you know, all possibilities, you know, which can occur. But say for n=1 potentials, Are there any results? Actually, I don't know any, more generic results, more non-trivial results. What happens if you go along a sort of non-compact direction along a potential valley, generically?
Yeah, so I think this classification of the cusps that we have for n equals 2, should somehow be translated to the classification of the types of potentials that we can have. So there should be a way to order and to have some order there. There are examples in the sense that, for example, like if we just consider M theory with G4 flux, the dual with type 2B with just G3 flux, we can apply, for example, the same theories that we use coming from Hodge theory to n equals 2. We can apply them to the flux, and therefore it can tell us how, you can decompose the flux on some components that are adapted to the singular limit, and there are just some possibilities, and this tells you also like the type of terms that you can have in your scalar potential, something similar to the types of behavior of the masses for the BP states. And if you study what are the properties that these theorems imposed on the scalar potential, it tells you that if you try to move along, for example, when you have some sort of runaway towards infinite distance, and we move on some on this direction, it's going to, what's going to happen is that the value of the potential happens along some mixture of the suction and the action, like the non-periodic and the periodic variable. And you can show exactly that it's always the same mixture, and so you always get the same type of value of the potential at any asymptotic limit. So there's a lot of structure as well that I think one can obtain, which is just based on having like asymptotic limits and discrete symmetries that have to be preserved, that this axionic symmetry have to be preserved.
It's obviously a very complicated problem, and obviously nobody has really this, but it's a short warning here, namely, it seems to me what you have said say are somehow deformed n equal 2 theories. If you have sort of an n equal 2 or whatever, and you switch on a flux, then actually your potential is a linear combination with integral coefficient of the periods, but these periods are still n equal 2 periods, still periods of the Calabi-Yau. But the actual functional complexity you can get in n equal 1 theories is much larger than this. Because there are many, the generic n equal 1 theory is not an hidden n equal 2 theory in disguise. Say with deep brains and open strings, you have new types of periods which have different behaviors, different geometry. So this cannot be captured in any sort of formulation which is based on n equal 2 structure. So our classification of it's much more complicated.
It's more complicated, but I think the qualitative features would remain. Because again, we are going to have these monodromies, if you wish, that are acting on the BPS charges of the membranes, right? Like we have a flux potential. We can understand it as the charge of some BPS membrane. And now we also have, these monodromies acting on these charges. The periods are different, I agree. It can be more complicated. So it's not that we're going to have the same types of limits, but I think there's also some order and some structure there that, we need to understand much better, of course, because it's more complicated.
Probably the physics will be similar or the same at the end, but still, if you talk about monodromies, in n equal 1 theories, you have, say, deep brains, open strings, you have open string moduli, monodromies then related to those, and you cannot approximate them or capture them with monodromies of the Calabi-Yau modular space. So there could be...
no, it's a different monodrome. It's not, they are not the monodromies of the Calabi-Yau,
So the n equal 1 story is always 100,000 times more complicated.
Yeah. But it's also, we have to get there at some point, right? Because, it's the next step, and it's also the one that is important to construct effective field theory models. And so,
I think now you want to take a break of 5 minutes. Now it was 9 minutes.
So, sorry, can I just ask a very quick question about what you said at the end?
Any question? If you have also other people more questions, go ahead.
So you said that it's somehow intuitive or obvious that that when you're at infinite distance, you have an infinite number of states, but also that when you're at finite distance, you have a finite number of states. Can you, why is it obvious?
No, it's not obvious. So it's really non-obvious to prove this. I mean, it's highly non-trivial. I'm saying it makes sense in the sense that, for example, if we think of the Schrödinger, of the modular space, that, I mean, we can think that we can understand the geometry also as the result of integrating out these BP states, so that we get the singularity when a BP state is massless, and also the surrounding of the geometry in terms of the integrating out. It makes sense that if we are integrating out, and I will show you later in more detail, but if we are integrating out an infinite number of states, then we are going to generate an infinite distance. While if we integrate a finite number of them, then we are never going to generate an infinite distance point. That's why, I mean, it kind of makes sense that there is this correlation, but it's based on this, what is called this emergence proposal. I mean, that you can understand the geometry as integrating out the states that are becoming light. It's non-trivial to show that this indeed happens, especially because it's very hard to keep track of the BP states around the modular space and to show how many you have and so on. So that's why for me it's a non-trivial check of these conjectures. I mean, to show that this is indeed what is happening. And that's why it's not trivial that at every infinite distance singularity you should have an infinite number of states. I mean, if you really try to prove it, I mean, it can be reasonable, but it's not. It's highly non-trivial.
Yeah, somehow that part seems slightly more obvious. Is the other one why?
The other one.
Yeah.
Yeah, let me say also that here you're assuming that these towers are weakly coupled. So it's not, of course, it's not true if, I mean, this is like a strongly coupled description, then, I mean, you could have finite distance and still like infinite number of things because they don't really count as infinite number of species. Like, for example, if we have a tensionless string, right? Tensionless string counts as infinite in many states, but actually only if it's weakly coupled. Otherwise, we can have a string that becomes tensionless at finite distance and engineer all the CFTs and so on, and that's fine. That's not in contradiction. But if it's weakly coupled, then there is this problem.
Okay.
More questions?
Irene, can I ask you a question about the CFT distance conjecture?
Yeah.
Do you know of any examples of CFTs where a singularity, either in the homological metric or in the CFT itself, develops at a finite distance in higher on the conformal manifold in higher dimensional CFTs, not in 2 dimensions?
Well, yeah, when you have a superpotential deformation, right? So, I mean, all the ones, the marginal couplings that are associated with gauge couplings, they are at infinite distance, indeed. But you can have marginal deformations associated to superpotential. And in those cases, they happen to be at finite distance. So for example, when you have an n=1 beta deformation of super young means or of other theories, that's a finite distance in the homological metric.
Thank you.
More questions?
Okay.
Yeah,
can I ask a follow-up question of that? So in that case, like what do you get at that finite point?
You don't get that free theory. Exactly.
Right. There is no specific, something specific.
Exactly, that's the point. So there is no higher spin enhancement or free sector or anything like that.
Mm-hmm.
It's just, and it's precisely because nothing dramatic is happening. Like it's just like a small deformation, and we also expect that conformal perturbation, right, theory is going to work when this parameter is very small and, I mean, nothing happens, while we cannot do that for when the gauge coupling goes to 0.
Right.
So does the Riemann tensor blow up on the conformal manifold, or some invariant blow up, or?
It's a singularity. Yeah, I mean, the symmetric, I mean, it has a singular point. It goes to 0. But it's something that you can resolve in the same way that here we resolve it with a finite number of states. There is also associated to something finite. Okay.